Today, we want to look at partial derivatives and more specifically using partial derivatives. Last couple of days, we reminded ourselves, not reminded ourselves, but we found out that we already have all the mechanics in play to find partial derivatives. When we have a function of two variables, there's just two derivatives to find. Whatever variable we're finding the derivative with respect to, we just hold the other variable or variables constant. So if we had a function of three variables, there would be three first partial derivatives in the x direction, in the y direction, and in the z direction. Or if those aren't even distances, if they're like angles or something, in the rho direction, in the theta direction, and in the phi direction. Just how much the function is changing in a particular direction. So right now we're still separating out our direction into just x direction and y. All we're doing is the same thing that we did way back in the day when we first learned about finding derivatives. So one of the things that we want to do with derivatives is find the equation of a tangent. So find the equation of a line tangent to the curve at a given point. And we're finding the equation of a line, which means we need two things. We need a point and a slope. So first off, find the equation of a line. This is telling us we need a point and a slope. Find the equation of a line. All a line is a location and a direction, a point and a slope. And then the next part of the problem tells us how we're going to do that. We're told that the equation of the line, we're told that the line is tangent to this curve. So since we are all well versed in the calculus arts, this part is telling us the slope of the line. So the slope of the line will be f prime at x naught. And when I'm saying at x, the point is when sentences are hard today. And finding the equation of the line tangent to this curve at this point, that's our location. So this is the point x naught and f at x naught, which is how we're going to get our y naught. Find the equation of a line is find a location and a direction and put them together in an equation. In this case, the way we're going to find the slope is with the derivative. And the point we find just by plugging in. So easy enough to do. We find the slope by taking the derivative. So f prime at x is negative 2x. And so f prime at 3 is negative 2 times 3, or negative 6. And that's going to be our slope. To find the point, we just need to find f evaluated at 3, and that's just going to be 4 minus 3 squared, or negative something. Now I've got a point, 3, negative 5, and a slope, negative 6. I can put that together into an equation. So we'll say y is equal to negative 5 minus 6 times x minus 3. The tangent line is the best linear approximation to the function near the point. That's why we do tangent line. This is the best linear approximation of the function near the point. So this is the best linear approximation of the function near the point. in the past, we could have used this to approximate what's going on at x naught, or at x naught equals 3.1 by noting our delta x will just be 0.1. So 5 minus 0.6 times 0.1. So negative 5 minus 0.6, negative 5.6. It's a little bit weird because we have such a simple function. Why don't we just plug 3.1 into our function and find out exactly what's going on at 3.1? But that's not the point. The idea is this is the best linear approximation of the function. The reason this is the best linear approximation is because linear function has only two things, a location and a direction. And this line agrees with the function in location and direction. A line has two things, location and direction. And this line, when we say best linear approximation, it does everything it can to behave like this function. So this matches, so the line matches the function in location and direction. This is the thinking behind tangent line. We're making a best linear approximation. We have to recognize that this is best by thinking a line has only two things, a location and a direction. So we grab the location and the direction of the function and use that to construct the line. Here we have the same question, but in a Calc 3 version, because instead of having just find the equation of the tangent, the line tangent to a curve, we want to find the equation of a plane tangent to a surface. The reason that we're doing this is that a plane is a linear equation in 3 variables, x, y, and z, whereas a line is an equation in 2 variables, x and y. To find the equation of a plane, we need the same information. We need a slope, we need a point and 2 slopes. So the way we're going to start thinking about this is that we need a point and 2 slopes. We're going to find a point and we're going to find 2 slopes, delta z over delta x and delta z over delta y. This is what makes the problem match what we had originally. We describe the slope with what's going on in the plane. In the back of our mind, we're thinking there's also another way to describe this plane with one direction, not the band, the vector that's normal to the plane. But we need a point and 2 slopes. The tangent part is what's telling us the direction, just like it did before, tangent to the curve. So our slope in the x direction will be fx at x naught, y naught. And our slope in the y direction will be fy at x naught, y naught. We need a point and two slopes. The tangent is what's telling us how to find those two slopes. And this is at the point 3, 1. So here's our point. I use the names of the things. And we will proceed in the exact same way that we did in the tangent line problem. I have 2 out of the 3 coordinates. I'll just plug in to find the third coordinate because we're working with a function, because working with functions is easiest. So I need 2 derivatives. I need an fx derivative. So with respect to x, 4 is constant. The derivative of negative x squared is negative 2x. And negative y squared is a constant term. When we're taking the derivative with respect to x, we treat y as constant, and it will either show up as a constant term or a constant factor. Constant term, the derivative is 0. Constant factor, it just carries on as a factor. So our slope is fx at the point 3, -1. So our slope in the x direction is -6. Not surprisingly, that's what this function looks like, 4 minus x squared for different values of y. That's going to be our slope in the x direction. We also have a slope in the y direction. Similar things happen. So copy, paste, edit, whatever I just said. I'll have the AI write that part. Then evaluates at the points. In this case, the 3 doesn't matter. It's the -1 that we care about because all the x went away. And so 2 will be our slope in the y direction, how z is changing in the y direction. Oh, I shifted colors. Oops. So we also need a point. So to find z naught, we'll just find f at x naught, y naught. So f at 3, -1. So it's going to be 4 minus 3 squared minus a -1 squared. So z naught will be -6, 4 minus 9. Now we're ready to put into our equation. Our function, thinking of the plane as a function, we start off at -6, and then we decrease by 6 in the x direction. And increase by 2 whenever y increases by 1. Our interpretation is the same that we had before. This is good because we're doing the same thing. We should be able to interpret it in the same way. We're doing the same thing. We should be able to interpret this in the same way. And that's what we do. This is the best linear approximation of the function near this point. In the same way that the tangent line is the best linear approximation of the function near the point. So if we looked at some small changes in x and some small changes in y, we can see that those values are going to be close to -6. If we try to approximate what's going on at 3.1 and we did not get a value that is close to -6, we would say something has gone horribly wrong. It's weird to ask that question considering we already know perfectly well what the function is. But if we take that function out, if we take that part of the description out, we can look at the numbers and figure out what's going on in the how z is changing with respect to x and how z is changing with respect to y, and use that to construct at least a linear approximation of what's going on near this point. Any questions? A lot of times we do math class kind of in a backwards fashion. I give you a function so we can use our tools to analyze the function. And it gives you this false image of how things work, where we're just going out and analyzing functions. And we're just handed functions, and then we analyze them. But that's not always the case. A lot of times what we're doing is looking at a big pile of data, and we don't know what this is. We don't know. We don't know what the function is supposed to look like. So we just start looking at the data and say, what's going on at the point? That's a 0-degree approximation of what's happening. Here's the data of what's happening at 3, -1. 3, -1, we get -6, whatever that means in terms of the data. Then we look at how z is changing in the x direction. We know we're trying to create a model where one variable is a function of the other two. So we say, well, what's happening if I change x a little bit? It looks like if x increases by 1, z will decrease by 6. And it looks like if y increases by 1, then z will increase by 2. Now we've gone from just a 0-degree approximation, the value, to incorporating the direction, one level of change. Now we've got location and direction. So in the same way that the line matched the function, the line matched the curve in location and direction, the plane matches the surface in location and direction. That's the idea of a tangent line. Any questions? How's everyone okay? For the most part, we just look at data and we see what the data is telling us is happening. Then we speculate about what's happening. It's kind of like the factorable polynomial thing that we talked about, that I mentioned briefly yesterday, where because of the way we set up the learning environment, it gives you a weird idea about what actually happens. So like we practice factoring polynomials by handing you dozens upon dozens of factorable polynomials. And it gives you this weird view of the world that most of the polynomials are factorable. And it is blatantly obvious that we've created a bias, because the thinking there is like, oh, most polynomials are factorable because most of the polynomials that I personally have encountered have been factorable. But we recognize that as kind of a ridiculous statement. And we say, my training has built a bias into my view. Same thing happens when we're dealing with these functions. We're trying to create models, and through calculus, I hand you the function and ask you to use the tools to analyze it. But we have to be able to work the problem backwards, because the function, this is just a model of something that we're trying to observe. Any questions? How's everybody okay? Everybody looks very disgruntled today. You all look like this. It's because problems was too easy. Well, why don't you try challenging us some, man? No one ever says the problems are too easy. No one ever actually says that the problems are too hard, right? Because as a math student, especially a calculus student, where you think you're all tough and you know a lot of shit, you're like, oh, I'm a calculus student. No problem is too hard. If I can't do a problem, it's because the teacher is being a jerk. Right? So the only time when you can't do a problem, it's because I'm a bad person, not because you need to practice more. It's okay to think that. I'm okay with being the villain in your story. If math is a struggle for you and you need a villain in your story, I signed up for that. I didn't think that when I first became a teacher, but I've come to realize, like, well, some students might need you to be the villain. You know what I mean? So I don't know if anybody, if you were planning on becoming teachers, like I said before, come talk to me and I'll talk you out of it. But I think every once in a while, they don't do it. They haven't done it for a long time, as far as I know, because I haven't watched the show. But every once in a while, The Simpsons absolutely nails it. And there is the one episode of The Simpsons. This was all before you were born, I think. There's an episode of The Simpsons where Bart nominates Mrs. Krabappel as Teacher of the Year. And so they show the selection committee for the Teacher of the Year, and they're watching all these videos. And it's a bunch of, and the one that they pick is a teacher that says, I like to use humor to connect with my students or whatever. And then they show him doing essentially Robin Williams from what was the movie? Dead Poet Society. And the people on the selection committee absolutely fucking nailed it, because they said, Dead Poet Society ruined a generation of teachers. Because that is 100% true. People watched Dead Poet Society and said, I want to be that teacher. I want to be Robin Williams in Dead Poet Society and be that super powerful as a teacher. They said, I want to do that. Then they forget that motherfucker had a writing team and was Robin Williams. Do you have a writer, a writing team, and Robin Williams, and a room full of students who also have lines? That's just like not how shit works. Like, everything would be great if all of you were handed a script at the beginning of the class, and then I had a script, then it would look like magic, right? But it's not. It's fucking work. But anyway, Dead Poet Society, good movie, ruined a generation of teachers because too many people that weren't teachers watched the movie and said, I want to do that. I want to be that guy. You might as well just watch Superman, the movie Superman, and say, oh, I want to be Christopher Reeves when I grow up. I want to like fly and turn time backwards by flying around the world really fast. Anyway. What are we talking about? Oh, yeah. I got to the end of the second example. That means I had to bullshit for a while to let this sink in. Let your subconscious get this out of the working memory so we can move on to something else. One of the things that we want to point out here is that a linear function has a location and a direction. And in this case, in the case of this plane, we have a location and two directions. We have a couple of ways to describe the direction. It's not really new, but it's kind of new because we don't do it so much when we have slope. Slope is just too simple to work with. It's too good. But if we rewrite our equation in a standard form, so if I write then I'll put the 6, let's see, I put this all on this side, so plus. If we rewrite the equation in standard form, we can see another version of point and direction, or location and direction. Location is still going to be 3, -1, -6. That's still evident in the standard form. But this is just another way to communicate location and direction. We've just got another version of location and direction in this form. We could still see the location the same way. 3, -1, -6. So our location is still 3, -1, -6. But our direction is now 6, -2, 1. That's a vector not in the plane, but perpendicular to everything in the plane. So now we have a normal vector for the plane. So rather than describing with two directions, saying the rate of change with respect to x is -6, the rate of change with y with respect to y is +2. We're still using location and direction, but containing the point 3, -1, -6 with normal vector 6, -2, 1. Because in 3 dimensions, if I define one vector, that takes up 1, it leaves 2 to be perpendicular to that line. Rather than describing with the dz dx. Oh, no, I didn't use that correctly. And say the plane is the span of these vectors. We're saying that the plane is everything perpendicular to the normal vector. We could do this before, but in R2, there's like the slope, rise over run, and then there's the perpendicular slope. And it's just weird to describe a line with a line perpendicular to the line we're trying to describe. But it makes sense in 3 dimensions because perpendicular to a line is an entire plane. So the other thing that we want to notice is that this description with a normal vector is something we could do with a line in R2, but it's not something that we would want to do with a line in R2 because we've already got away from Charlie array. Any questions? Yes. The normal vector can be wherever we want it to be. So the 3, 1, 3, -1, -6 says take that normal vector and put it at that point. So go to 3, -1, 3, -1, -6, and then put the normal vector there, and then make sure that'll make sure that the plane goes through that point. Any other questions? Another way to write the standard form is to multiply everything out and not have the point, not tie it to this point. So I run out of space. That's all right. So I'll have 6x minus 18. So I'll have a 6x minus 2y plus z. And then take all the constant and summarize all the constant over here. That means I have to do arithmetic. Watch out. -18, -2, +6. So -20 plus 6 is -14. So that'd be a +14 over here. That would be a different form, a different description of the same plane. The advantage of this equals 0 version is that one point is super obvious, which is not the case down here. Any questions? Comment? Smile, Lamar. How's everybody okay? Everybody looks so very sad. We're almost done with week 4. There's only 13 weeks to go after this. And one of them is Thanksgiving week. So it's like only 3 days in that week. So I don't know what y'all are complaining about. I noticed something once when I was a student. Oh man, because my friends and I, when we were undergraduates, we all agreed that we just wanted to get out of school. Then at one point, my friend Jason, who was damaging to my mental health. Jason, if you're out there, you are damaging to my mental health. He's like, "Oh, why are we so concerned about getting out of school fast?" And then it's like, "Oh, well, so we can." Then it occurred to us, so we graduate, so we can get a job. It's like, well, why do we want to do that? So we can make money, so we could buy things, so that we could retire comfortably, so that we could die comfortably. Always to the next thing we're looking, right? And we've gone so far as to inflict this kind of thinking on children. It's so fucked up. You got to get into a good high school, so you can get into a good college, so you can get into a good graduate school, so you can get a good job, so you can have a nice retirement, so you could die. Whoa. Then we'll watch Empire Strikes Back. And listen to it. Almost to the future, this one's looking. Ever thinking about where he is? Mm-hmm. What he's doing? Mm-hmm. Yeah. Anyway, probably shouldn't grab so much philosophy from such a dopey series of movies, but there it is. That's what happened. All right. So important thing to note is that we're doing the same thing that we did before. The thinking behind it is the same as we had before. We're trying to find a linear equation that matches in location and direction. The reason that we're going for that is that's all that a linear function is. A linear function is just location and direction, point and slope. It's two slopes in the case of a plane. And if we have a tangent, I don't know, three-dimensional solid to a function of 3 dimensions, I don't know what that would look like because it's in 4 dimensions, but we would do the same thing. This would be the same if I had a function of 3 variables at a point with 3 points. We would do the same thing. We need a point and 3 slopes. We would put it together in the exact same way. There would just be another term out here. And once we get to 4 variables, it'd probably be x1, x2, x3, and x4. Because we're like started too close to the end with x. Any questions? So what's missing right now is another example that I had that was supposed to take up the next 8 minutes, but it's gone. I don't know what happened to it. Because I'm like, oh yeah, I'll do this, and this. That'll take the hour, and then we'll dismiss, come back on Friday. And I don't know what it was. So that's going to do it for today. I will see you all on tomorrow. Probability of me remembering what that example was, close to 0. How weird. I lost 8 minutes. Oh well. My loss is your game. That's it for today. I'll see you all on tomorrow. Everybody have a good day. And thanks for playing.